Okay, I'm not sure why I thought that was the end when there's one more question, number 9. Number 9 says 1,000 kilogram satellite, so the mass of the satellite is 1,000 kilograms, is put into circular orbit above the Earth, so it always remains over the same place on the Earth. So when it always remains over the same place, it means it's a geosynchronous satellite. So the mass of the Earth, we know, is 5.98 times 10 to the 24th kilograms. And then we also know that the period must be 24 hours. Okay? And the question wants to know the radius of orbit and a whole bunch of other things. But A, radius of orbit. So with these givens, I would use... I'm not sure what's going on with the color here. It's like blue. With these givens, I would use Newton's version of Kepler's third law. So I would use r cubed of the satellite over t squared of the satellite equals g, mass of the central body, which is the Earth, over 4 pi squared. Okay, bring your t of the satellite squared up. So you'll have r cubed is equal to g, mass of the Earth, t of the satellite squared, over 4 pi squared. So 6.673 to the negative 11 Newton meters squared per kilogram squared. Mass of the Earth, 5.98 to the 24th kilograms. And the period is 24 hours, which you have to switch to seconds, 86,400 seconds squared, divided by 4 pi squared. Okay, and what you get is r cubed. So when you do this, you get an r cubed of 7.5455, I think, times 10 to the 22nd meters cubed. Take the cube root, and you should get the radius of the satellite to be 4.22568 times 10 to the 7th meters. Now, you could have also done it with r cubed over t squared for the satellite equals r cubed over t squared for the moon. I just did it this way because I knew the mass of the Earth, and I didn't have to look anything up then. If I was using the moon, I would have had to go to my chart, and I just didn't want to. If you do use the moon, you get a slightly different answer. You get 4.212 times 10 to the 7th, and that's just because of, these are huge numbers that we have rounded in our chart, so they're not 100% accurate to every digit, right? We aren't looking at significant digits here. So the second part says, what would be the satellite's weight in orbit? So you're looking for FG then, and that's G m1 m2 over r squared. Whoops, and this would be a big R. So 6.673 to the negative 11 Newton meters squared per kilogram squared. The mass of the Earth, 5.98 to the 24th kilograms. The mass of the satellite, 1,000 kilograms. And then over the R we just found, 4.22568 times 10 to the 7th meters squared. And when you get this, now I think you get 223.475. And I think that's using this radius. I'm trying to figure out which radius I use there. Newtons. Okay? That's B. And then C says, how fast is it going? So you have a couple of options. You could use V equals 2 pi r over t. So 2 pi times the r you found up there, 4.22568 times 10 to the 7th meters. So assuming you didn't screw up that r, and what was it? 86,400. You could also do v squared equals gm over r. 6.673 to the negative 11 Newton meters squared per kilogram squared. Not going to have enough room. 5.98 to the 24th kilograms. And then divided by that 4.22568 times 10 to the 7th meters. And remember, that's v squared. The other thing you could do, you could set this equal to mv squared over r, multiply by r, divide by m. It'll end up looking not like this. Yeah, when you cancel things out, it would. In the end, you should get something around 3,073.00. And it'll be close to this. It will depend on which route you went. I think I went this route. Because I had this in my calculator, I multiplied by the r and divided by 1,000, which would really then should be this answer, right? Because if I multiply by 1r, yeah, so that's what you get if you do it this way. This one will probably be a little bit different, all right? And now that's the end except for the practice assignment.